Yeah, what we're going to talk about today is a little research project that we've done recently here at Integrus Architecture. We called it Mass Timber High because we wanted to test, get our feet wet with working with embodied carbon. And we've been doing some benchmarking on some past projects, but we wanted to take a bigger stab at it. So we decided to look at one of our recent high school projects. It was a 3-story K-12 high school, and redesign it with mass timber. So we took the original design, which was a type 2 steel frame, moment frame building. And actually, excuse me for a second, I'm going to change my screen here a little bit. There we go. So we took the original design, which was a steel frame building, and substituted mass timber. The reason we chose this project to some extent was we wanted to look at substituting mass timber for a type 2 building. We have lots of 2-story buildings and some of them are in type 5, but we think the real savings or the potential savings in embodied carbon or greenhouse gas emissions from embodied carbon come from substituting steel with mass timber. So that's why we chose this project. We did a complete cradle to cradle life cycle analysis. Of course, the real savings come through the product stage, transport, construction, and then end of life, and actually in the recovery stage. That's assuming that you're including carbon sequestration from biogenic carbon in the project or in the LCA boundary. And we did choose to do that. This, of course, is a topic that everyone understands at this point is fraught with complications and uncertainties. There's lots of really interesting research on upstream effects of forestry that, of course, need further study. So we thought seriously about that. About, does it make sense to include biogenic carbon and the sequestration of biogenic carbon in the project? And there is some research out there that supports that idea, and there's some research that suggests that maybe a more conservative approach is warranted. We think that it's okay to be optimistic and hope for the best, move fast, but be careful about what you break. So we decided that for this study, we're going to take a look at including biogenic carbon with the understanding that there's still uncertainty that needs to be resolved. We looked at 3 scenarios. The first one we're calling the baseline, which was the building as designed. It's at about 230,000 square foot, 3-story high school. As I said, it's a type 2 building, steel frame with lateral moment frame systems. For the mass timber alternates, we looked at 2. We're calling them alternate A and B. Alternate A is just a glulam frame system substituted for the steel frame in the baseline, and it has a mass timber composite floors with a mass timber and gypcrete topping slab. Alternate B has a similar frame structure, but we're also using CLT rocking walls for lateral and CLT bearing walls, both interior and exterior. We did that because we wanted to see what the implications would be for increasing just the quantity and the presence of timber within the building, what the impacts would be to both the quantity of fiber, the embodied carbon emissions, but also the character of the interior of the building is something that we're concerned about. I should say that one of our motivations here in working with our K-12 clients is to study and then demonstrate what the impacts are of using mass timber on accommodation of educational programs. It's extremely important in designing learning spaces in K-12 programs that there's a great deal of flexibility in the plans, especially between learning settings, between classrooms and what we think of as breakout areas or shared areas. And the flexibility both is something that's needed on a daily basis in terms of connections between these spaces and multifunctional utility, but also the ability of the building to adapt over time as learning models and teaching and educational pedagogies change. So we wanted to be able to first understand what the impacts of mass timber would be on the educational program, and then be able to demonstrate those effects to our clients as we hopefully work with developing mass timber on some of our future projects. So those are the three scenarios that we examined. The baseline floor plan is on your left, and the floor plans for the alternates are A and B are on the right. We did some minor modifications to the plan for a couple of reasons. One, we wanted to make sure that we were absolutely minimizing the quantity of timber or fiber that we would use. So we simplified the geometry a bit, particularly in connections, so that the sizes that we're using are conforming not only to optimal manufacturing sizes for glue lam timbers and CLT panels, but also that those sizes which would dictate the structural, or rather the planning grid for the classroom layout, that those would work with a standard classroom module. And we determined that they would if we went with a modified grid of 30 feet square, as opposed to the 26 by 32 foot grid that we did in the original. It's a minor modification. It doesn't really result in any changes in area or building size, and it still does work extremely well with the accommodating the classroom settings. So those are the changes. One thing we did keep the same was we have some high bay spaces in a significant portion of the building. We kept those as they were designed. So it's not actually an entire building study. There's about 25%, maybe 30% of the, well, 25% of the floor plan that remains as it was in the baseline, which is still a type 2 structure with moment frames. And now let's get to the results. We used a Revit model, and all of our material quantities came directly out of the Revit model. We did the analysis in Tally, again, inclusive of biogenic carbon. And so you can see the analysis here, looking at foundations, above grade structure, the envelope, and then what we're identifying as the biogenic carbon credit that happens in the life cycle stages A and D. So the results are I guess not surprising. Others have demonstrated similar effects. There's a reduction in greenhouse gas emissions for alternate A of about 45%. That's both the just the reduction in emissions from using timber, but also the substitution effect of not utilizing steel in the construction of the building. And alternate B, that delta between the greenhouse gas emissions from timber to steel is more like 48%. So it's extremely significant. We also wanted to track it in some different ways, which Tally allows you to do. We took a look at, what's just happening with the timber movement from sequestration to ultimate release. You can see that in product stages A1 through A3, when you take that sequestration credit, if you will, there's a significant reduction in greenhouse gas emissions. Those, again, are ultimately released in the end of life stages. However, there's about an 8% sequestration of that timber or biogenic carbon over the life of the building, or at least between product stages A1 through A3 and C2 through C4. So that was just another way we wanted to look at the data to understand where the changes, where the savings or the reductions are occurring. So that's the result, or the sum of our results. It's pretty straightforward. There's not a lot more to say about it other than the fact that I've already mentioned the uncertainties associated with the biogenic carbon. I'm going to end on a personal note. I think we're all pretty much here on the same page about the need to find any way we can to improve the performance of our buildings and reduce carbon emissions as professionals. On a personal note, this is a forest that I've hiked in over the years throughout my life. It's a place that I love dearly, and it looks like this now because of wildfires that occurred a few years ago. And I know that probably many of you have similar experiences. And so for me, it's just a reminder that this is both a personal and a professional mission to make the world the way we want it to be. And that's the justification behind this effort. So with that, I'll open it up to questions or comments from anyone who has anything they'd like to share.
It looks like there is a question on how the flooring assembly, mass timber CLT with gypcrete, was designed to enable the separation of the CLT and gypcrete at end of life so that the CLT can be reused and not go to landfill bonded with gypcrete and decompose with potential methane release.
That's a great question. We didn't get into that level of detail in thinking about design for deconstruction, but of course you would absolutely have to. So I wish I had a better answer to that, but definitely something that would ultimately need to happen. This was really a kind of a high level study for us, looking at the greenhouse gases only, but certainly in the detailing and the final design, that's an important issue.
If you were to redo a similar study for a different building type, what would you do differently?
Good question. Not sure. I think one thing we would do differently maybe is make sure that it's 100% apples to apples. I'd like there not to be any uncertainty about differences between the models being studied. And maybe I would like to make it truly a whole building study. This is just, as I said, foundations, envelope, and structural frame. I think we know that interiors are a huge portion of potential emissions and of material, and especially when you include renovations that happen over the life of a building. So I would think that the next step would be to include interiors as well.
For K-12 projects, future flexibility of spaces without conflict to major structural systems is an important consideration. Do either of the alternate studies impact future flexibility?
Thank you for asking that, because I meant to talk about that. As it turns out, they don't really. There's a minor difference between the alternates B and A in that when you use the CLT for bearing walls and for lateral, you are reducing the size of openings and the location of openings that can be created in those walls. So of course you want to control where the lateral elements are placed, but there are conditions or situations where lateral CLT walls do separate a classroom from an adjacent shared area where you want maximum connection and flexibility. And there is some reduction both in visibility and an ability to move between that, across that boundary. So, but it's not significant because it's not the case that you have so many of those conditions that it becomes a significant impact. With the glue lamp frame substituting steel, there really was no difference because we're still using a lateral system of brace frames in those conditions. So the only difference really is a minor difference with the CLT.
Mark is asking if anyone is familiar with end markets for mass timber at end of life. So has anybody seen any reuse of mass timber or a market for it? And while we're waiting for that answer, Vikram is asking, how far out do we consider end of life for these projects?
It's interesting to think about that. We assumed a building life of 60 years in this study, but if we were to expand that to 100 years, and I think that might be a very reasonable thing to do. I mean, why can't we design buildings that last 100 years? Then the question, it seems to me, of sequestration at least is put off until 100 years from now, and then we buy time. And one of the things we need in controlling carbon emissions is time to develop new solutions and better technologies. So I don't know if that answers your question, your comment or question, Vikram, but I think it does make sense to think about, designing buildings to last much longer than they typically do, or than we have in the past.